All right, so let's take a look at this. So let's say we have 0.14 moles per liter of ammonia at equilibrium with this much nitrogen. What is the equilibrium concentration in the reacting mixture? And they're giving us the K value, right? So we have 1.7 times 10 to the 2 is equal to, we have 0.14 squared over, so we're looking for H2, so our N2 was 0.02, this is a 2, and then of course we have X to the 3, right? So essentially I'm just plugging in X. You can leave this as H2. It doesn't matter to me. So at this point, right, we would basically be rearranging to solve for X. So again, this can be done in multiple steps. However you would like to show this, you can go straight from here to your final product. So just be mindful though, that when you're doing this, you would take, because this is X to the 3, you would have to take the cube root to eventually get to your final X. So it's 0.18 moles per liter. So because we're dealing with, we are representing a concentration, of course we know it's going to be moles per liter at the end of the day. So like I mentioned before, so just like we did with that the second example here, what does a larger K value mean? The further a given reaction progresses to the right to achieve equilibrium, the greater the equilibrium constant is, right? So of course we know that because K is our products over reactants, right? So it's just a matter of comparing the amounts at equilibrium. Okay, but there's a few things to keep in mind when you're doing this. So this is in general, okay? But the KEQ value alone may not tell us information about the percent yield. So just because you have a very large K does not mean you can make the assumption about what the percent yield is. Okay, so just something to remember here. So if I have a K value of, 45 versus, 40, there's no, it's not like, oh, well, this one has a 5% greater percent yield. Well, no, you can't really tell by looking at just the K values itself. Okay, so the K values, an equilibrium's position will depend on the K value as well as what the concentration is of your initial reactants, which should make sense, right? So your percent yield for the reaction is going to be unchanged, but remember that your concentrations that you begin with will eventually change what your concentration are of your products. So if you have 30% yield, yes, but your 30% of different concentrations will give different product numbers, even though at the end of the day, your percent yield is the same. And two reactions with the exact same KEQ at different temperatures and the same initial reactant concentrations can still have different percent yields. So if I have two reactions, let's say one has a K at 20 degrees of 45, and I have a different reaction and the K at 30 degrees is also 45. That does not mean they have the same percent yield, okay, even if they start with the same initial reactant. And that's simply because they're going to be different reactions. They're not the exact same. They're saying if you have two reactions with the same KEQ, that doesn't mean necessarily you have the same percent yield, especially due to the fact that it's at different temperatures. So I guess you can make this assumption if you're comparing the same reaction at different temperatures. If you have different temperatures for different reactions with the same K value, that's not going to be enough to tell you the information about the percent yield either. Okay, so just something to keep in mind, that the K doesn't really give us everything, I guess is like the bottom line to that. So let's talk about how does the K value change when equilibrium shifts occur. So going back to Le Chatier, right? So looking at different stresses that could be added. Well, the only stress that will change the KEQ value is going to be a change in temperature. So KQ, yes, it's dependent on initial concentrations, but it will only change depending on the temperature of that reaction. Okay, so take a look here. So we have an exothermic process where we are with a forward and reverse reaction. So let's say we were to add reactant. This is kind of a nice review of equilibrium shifts. But if we were to add reactants, it's going to shift to the right. The equilibrium position may shift left or right, depending on the amount that this was done. But your equilibrium constant is no change. That's the focus here. Decrease in volume. Okay, well, we have here 3 moles versus 2 moles. So if we have a smaller space, right, that means our pressure is increasing. It's going to shift to the side that's going to occupy less space. So shift to the right. So the equilibrium position here, of course, will shift to the right because we are making more product. And here we go. The K value will not change. If we were to decrease the temperature, for an example, right, because this is exothermic, it's going to shift to the right to try and replenish that lost energy. And because we're making more product, in that case, we're going to have an increase in the K value. So if we were to increase the temperature, it would have shifted left, meaning that your K value would actually become smaller because there would be more reactant produced. Okay, so this is just kind of a little bit of review, but the main thing is that the only thing that can change your K value is the temperature that your reaction is happening at. All right, so let's take a look at what if we wanted to know what the K value would be for the reverse reaction. Okay, so technically, the K expression here would be my NH3 squared over N2 and then H2 to the power of 3. Now, if we wanted to do the reverse reaction, we would basically be flipping this because, and notice anytime we're talking about reverse, we always put this little like apostrophe here. So that would be my, if we were looking at the reverse, it would be like as if this is our reactant and this is our product, right? So we'd have N2H2 to the 3 over our ammonia. So they're basically reciprocals of one another. Now, anytime you are asked to write out the KEQ for a reaction, you are always assumed that you are looking at it from left to right, unless you are told specifically to write the K expression for the reverse reaction, okay? You are always assuming forward unless told otherwise. So to calculate your K value for the reverse, it would just really be the reciprocal of what your K value is of your forward, right? So let's say your K for the forward reaction was 25, right? Your KEQ for the reverse reaction would be 1 over 25, right? So when you're, let's say you have this value that's given to you and you're asked to solve for this, that's essentially what you would have to do. So it's pretty straightforward. Okay, so this is the last kind of concept. Let's see, I lied. Did I lie? I think this is the last concept that we're going to be looking at today. So we're determining the direction of a reaction. Okay, so when you have an equilibrium equation, right, we know we have the forward rate equal to the reverse rate, and we have our concentrations that are kind of unchanging, right? Like when you have a graph, it looks like it's a continuous straight line. Sometimes you will be given scenarios that are not at equilibrium yet. Okay, so a typical question would be like, oh, here are some concentrations. Is this system at equilibrium or not? So when you are unsure about the conditions of your system, like you're not, basically, let's say if you have non-equilibrium conditions or you don't know if it's equilibrium, we have a new value that we're going to be using called a Q, or reaction quotient, or we call it a trial K. So meaning it's like we're going to do a K expression, but we cannot call it a K expression because K expressions are only for equilibrium. So we're going to put in this trial K, which is Q, and the difference is instead of it being equilibrium, you can put in any concentration. because remember, the whole purpose is that it's a trial. We don't know if it's equilibrium or not. So from our results, from the calculations of our Q, we can actually determine if it's in equilibrium or not. And if it's not in equilibrium, we can determine, well, what will happen for it to get there. So remember, Q is like your trial, like you're not sure. So if we plug in concentration numbers and the Q ends up being equal to the K, that means it was actually really in equilibrium. Okay, like the concentrations you put in were equilibrium concentrations. You just didn't know it yet. If the Q value, your trial, is bigger than the real value, what that means is there essentially is too much product at that moment in time, because it's still set up in the same way. So if we have a number here that our answer is too large, that means in order to reach equilibrium, it will have to create more reactants again. Like it'll have to lower the amount of products made. If it's the opposite and the Q calculation is actually lower than what the K value is, that means that there is not enough product yet for it to be considered in equilibrium, which means that it would shift to the right. The forward reaction has to go faster in order for equilibrium to be established. So the main difference between Q and K is really if you're not sure about if the conditions are at equilibrium or not. And because we have this knowledge, if we know what K is, we can start making predictions as to what will happen in order to get to equilibrium. So here's just kind of like a visual representation. So if your Q is equal to your K, that means you have equilibrium. If your K value is too big, that means there's too much product. There will have to be a shift to the left to make more reactant to get to this point, right? We want to lower the Q number to make it equal to K. And of course, if your K is larger than your Q, that means there's not enough product there. There's too much reactant under those conditions. So we'd have to shift to the right to increase our Q by increasing more product. So maybe this is not making a whole lot of sense until we start looking at some calculations. All right, so here we go. So again, if you'd like, you can pause the video. I may have to take a third part into this, depends on how long it takes me to get through this. But pause the video, try out the next 3 questions that are in your text, and then we can see how you did. Okay. So for this first one, it says, an industrial synthesis of hydrogen involves the reaction of steam and methane to produce a synthesis gas, which is a mixture of hydrogen and carbon monoxide. And they're giving us the K at that temperature. A mixture at that temperature contains these concentrations. So notice it does not say that this is at equilibrium. It just says at that temperature, we have these concentrations. In which direction will the reaction proceed to establish equilibrium? Okay, so we're going to have to use Q because we are not sure if this is in equilibrium or not, right? So it's products over reactants. Everything is a gas here, so everything is going to be included. All right, and I'm just going to put to the side here that we have our K value is 4.7. So you would literally plug in these numbers the same way you would plug in for your K and then compare it at the end. So we have our carbon monoxide, our hydrogen, our ammonia, methane, and water. Okay, so when you calculate this Q, we get actually 2.4, which is smaller than the K. So what this tells me is that there is not enough product in this scenario of concentrations for it to be at equilibrium. So for this particular reaction, we would have to shift to the right in order to reach equilibrium, to get the concentrations of our product to be higher. Okay, so let's try out the next 2 in our part 3